Recently, I have seen some students misunderstand one property of the D'Alembert operator. In particular, the D'Alembert operator is usually denoted with this symbol, the box letter, whatever you want to call it, and it represents in Minkowski space-time derivatives of second order, and in tensor notation they can be written like this, for example, d mu. So this would be d0, and then you have the special dimensions. So here you get minus, basically you get the del symbol squared, so it's the gradient squared, or if you want, the Laplacian in 3 dimensions. And this would be, if we assume that the speed of light is equal to 1, we can use units such that the speed of light is equal to 1. This would be partial d over dt squared, right? And therefore this can also be written as d over dt squared minus d over dx squared minus d over dy squared minus d over dz squared. So this operator is actually important because in physics it appears so many times that basically it's even very difficult to count them. Anyway, what I want to discuss is the following. So if we apply the D'Alembert operator to a product of functions f times g, so these functions are functions that can depend on time and space. So they can depend on the time dimension and spatial dimensions, whatever number of dimensions you have. I have seen more than one students write down this identity. So maybe they didn't even notice that this cannot be true. But first, let me write it down, and then let's discuss it. So they treat this operator just like a derivative, basically. So you have the D'Alembert operator applied to f times g. So you have this plus, and then you have f, and then you have the D'Alembert operator acting on g. But the problem is that this is not true. This is wrong. And let me show you why. It's quite easy, quite simple to show that if we simply use the property. I mean, this is not the property, this is the definition of the D'Alembert operator. So if we write down these derivatives instead of the symbol itself, we can realize that what we wrote here is actually wrong. And that's easy. So first, let's apply this derivative to the product of functions. We know how to apply a derivative to a product of functions. We have d mu f acting only on f times g plus f, and then we have the derivative acting on g. And then we can apply d mu here outside of this parenthesis. So we have d mu f g, and then this can also act on g here. So we have d mu f d mu g plus, and then we have to take this into consideration. So we have d mu f d mu g plus f d mu g. Now, according to the properties of tensors, we can also, for example, rewrite this as d mu with the lower mu, and of course we have to raise this one. So we have d mu f d mu g, and then you can see that this quantity here appears twice. So this will give you twice d mu f d mu g. Whereas you can see here that you have the D'Alembert operator acting on f times g, and here you have f times the D'Alembert operator acting on g. So you can see that actually the formula is wrong because apart from these two terms that indeed appear in the final formula, we have an additional term here that's given by these derivatives. So these mixed derivatives, if you want. And sometimes in index-free notation, this can also be written as twice, and then you have d without any index f, and then you take some dot product with g. So this dot product must be intended as a product in Minkowski space. So you have a signature there, either plus, minus, 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 or in some other cases it can also be defined with a different signature. So it depends on how you define these objects. So in this case, I have used the signature plus, minus, 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 but this is actually a convention, and if you consult different books, you might have different conventions. But anyway, this is just to show you that sometimes notation can trick you. It can deceive you if you don't think about it in in a more basic notation where you can actually derive the final formula without any problems. So this is something that I just wanted to show you. It's actually quite simple, but it is just to show you that sometimes even simple mistakes can happen if you do not if you do not check your calculations quite well.